My name is Duilio Santis, and my presentation will focus on the generation and dynamics of a certain class of nonlinear excitations known as breathers in non-Josephson junctions. A Josephson junction can be constructed by sandwiching a thin insulating layer between two superconducting materials. A description of the system can be given in terms of simple macroscopic wave functions, and the well-known Josephson equations can be obtained. The first one gives us the tunneling supercurrent as a function of the sign of the phase difference between the pair wave functions, and the second one tells us that the time derivative of the phase difference is proportional to the voltage drop across the junction. A non-Josephson junction is a device which has a length parameter which is much larger than a characteristic length scale known as the Josephson penetration depth, and a width parameter which is much smaller than that. In particular, the overlap geometry is shown here. By taking a combination of the Josephson equations with the Maxwell equations, we see that the dynamics of the system is governed by a perturbed version of the sine-Gordon equation. Here, time is normalized to the inverse of the Josephson plasma frequency, and space is normalized to Josephson penetration depth. Also, alpha is a damping parameter which takes into account the effects of the normal electrons, which might be present in the junction at finite temperatures. Gamma is a constant bias current, and this term right here is a stochastic contribution which mimics the effects of thermal fluctuations in the system. Finally, the boundary conditions are given by the value of the external magnetic fields at the boundaries of the junction. Before looking at the more complex perturbed equation, let us classify the fundamental solutions of the pure sine-Gordon equation. In the linear limit, we have plasma waves, which are characterized by this dispersion relation, which tells us that no linear waves can travel for frequencies less than 1, so the medium possesses a forbidden band gap. The simplest solitonic solution is the kink or anti-kink, and they have a clear interpretation in the context of long Josephson junctions, since they exactly carry a quantum of magnetic flux phi naught. Breathers are essentially kink-anti-kink oscillatory bound states. They have this additional degree of freedom, a proper frequency omega less than 1, and we study them because they have not been observed in long Josephson junctions yet. The solitons can be quickly visualized. In particular, kinks and anti-kinks are essentially 2 pi steps of the phase along the junction. And here we have a moving kink as a 2 pi twist along a chain of elastically coupled pendula, which is a mechanical analog for the sine-Gordon equation. Here we have a stationary breather and a moving one. As you can see, they are localized in space and they oscillate in time. And this is a stationary breather in the mechanical analog. By virtue of the robustness of the solitonic profiles, we are able to make use of them also in our case. In particular, it is interesting to look at the effects that different perturbation terms have on soliton dynamics. For example, a damping term tends to slow kinks down, while a bias current accelerates kinks and anti-kinks in opposite directions. For breathers, we know that a damping term makes them unstable. In fact, they decay into radiation with an expected lifetime of about 1 over alpha. Also, a bias current tends to disrupt this oscillatory bound state. We propose a new generation mechanism for breathers in long Josephson junctions, which makes use of magnetic pulses with frequency omega less than 1. We take a pulse which is shaped like this with a typical amplitude, Gaussian switching on and off regimes, and this time right here at which the shutdown of the signal begins is not fixed, but it is adjusted in order to produce single breathers in the junction. Essentially, here we're making use of a phenomenon which is called nonlinear supratransmission. In this frequency amplitude plot, 2 things can happen. For low amplitudes, since the linear approximation holds, and since we are forcing the medium in its forbidden band gap, no energy can be transmitted in the medium. However, for strong enough amplitudes, a completely new regime may be unlocked, and the energy transmission can be supported in the form of purely nonlinear modes. This is actually called a bifurcation diagram. In order to explore our approach, we need to be able to tell whether only breathers are generated for a specific frequency amplitude combination. To do so, we developed several breather detection criteria. The first one, we call it the phase criterion, is based on the idea that breathers decay under dissipation while kinks remain stable. The second one, we call it the voltage criterion, makes use of the fact that the rapid breather oscillations produce practically null in voltages, and we saw that a perturbative estimation of the energy transmitted to the junction can also be used as an effective breather detection technique. Our results will be given in the form of refined bifurcation diagrams. In particular, the light gray color indicates region in which no energy transmission is supported. The dark gray color is associated with points with at least a kink in the final state of the junction, and the colorful regions, depending on the criterion in use, are the ones in which only breathers are generated. A first interesting result here is that significant only breather regions exist in the omega A space, and also it is interesting to note that the two criteria give us very close results. The effect of a damping parameter is essentially to extend these only breather regions. In fact, and this is understandable since the oscillatory bound state is more easily formed for higher values of the damping coefficient. Thanks to our generation process, we were also able to study the breather decay mechanism. In particular, by tracking its decaying amplitude and by means of an exponential fitting procedure, we assigned a lifetime to the excitation, and by doing so for different values of the damping coefficient, we matched the perturbative prediction. The effect of a bias current is to destroy these only breather regions, and this again can be understood by means of perturbative arguments. Finally, we looked at the effect of a stochastic perturbation. Due to the extent of the computational task, we focused our attention on one of the only breather regions detected in the deterministic case. We defined an only breather generation probability, and we estimated it for a certain number of realizations. As you can see here, in correspondence of the only breather region deterministically identified, we see high probability cores, which is a sign of the robustness of the process. And also some sort of noise-induced widening of this structure occurs. We can look into that in a little bit more detail by considering two specific omega A combinations. If we take a combination which belongs to the deterministic region, we see a monotonically decreasing behavior. However, if we go outside of this region, we see a non-monotonic behavior, which is very interesting. So we looked at the generation and dynamics of breathers in long Josephson junctions in the context of the nonlinear supratransmission effect. We documented the presence of significant only breather regions in this parameter space, and we studied the localization and the properties of the emitted breathers as a function of the system parameters and noise intensities. So thank you very much for your attention.